Hi, everyone. Welcome. Thank you for joining us in our live webinar to celebrate the International Day of Light, which is this May 16th. Today's speaker is Dr. Tom Schad. Dr. Schad is an associate astronomer at the National Solar Observatory and is actively involved in the Daniel K. Inouye Solar Telescope project. He's been engaged with the telescope ever since completing his PhD at the University of Arizona in 2013, first as an instrument scientist at the University of Hawaii, and then as part of the NSO. His research focuses on using polarized light to help answer the question of how the sun's chromosphere and corona are heated and how they release energy into our solar system. When not studying the sun, he likes to spend time on the beach or in the woods with his family. And so with that, welcome, Dr. Schad.
Oh, thanks, Tashana. Thank you so much for the introduction and a very warm welcome to everyone joining us today for this talk. It's really quite a pleasure to have this opportunity to talk about capturing light with the largest solar telescope on Earth. In fact, the largest solar telescope ever built. And this is, of course, the Daniel K. Inouye Solar Telescope, which is located on the island of Maui. It's been under construction since about 2012 and is very close to being very full operational, and we're getting very excited about it. This talk is being given in celebration of the International Day of Light, which is a day recognized by the United Nations Educational, Scientific, and Cultural Organization, or UNESCO. And what it is it's a day for us all to appreciate the importance of light in our daily lives, as well as a chance for us all to learn about new developments in light science and in light technology. Light has always been fundamental to our way of life, and now it plays even a more important role, especially when you think about communications, sustainable energy, medicine, agriculture, or its use in cultural and arts, in the arts. In that context, to speak about a solar telescope makes a lot of sense. Studying the details of what makes up sunlight itself has historically led to many of the key breakthroughs in how we understand light, especially how light is created and how it interacts with matter. Today, we continue to study how light interacts with matter, both as a way to collect sunlight and or use light on Earth, for example, in communications, medicine, and so forth, but also to learn about processes happening on distant objects, basically anywhere that light is emitted from in the universe, and that includes our sun. So today, to get us started, I'd like to cover just a few basic facts about light and about sunlight in general. So here are a few basic light facts to get us started. So light, as you may know, as many people know, is a kind of energy. So sunlight is energy. Anytime you sit in the sun, sit on the beach, get a suntan, you know that the sun has a very energetic, is very energetic, and it can really, lead to a suntan or heat you up on the beach. It is a very, very powerful source of energy in our lives. In fact, if you think about all of the input of energy into Earth, into, for example, the Earth's climate, every source of energy, if you add them up and you create a budget of it, sunlight provides 99.973% of that energy. Maybe you can think of a few other energy sources that lend to that energy. There's a few. The next most important one is radiogenic or radioisotope decay in the core of the Earth. That also provides energy into our climate system. Now, light is a very strange thing, and it's in fact it took a long time to understand really what light is and to describe it. Light is funny in the sense that it's both a wave. It has wave-like characteristics. It's a wave of electric and magnetic energy, but it's also a particle. It's discrete. It has a very corpuscular character to it. And when we talk about light particles, we often think about photons of light. And the energy of these light particles is in fact discrete. It has a particular value, and it's related to its wavelength. So even though you see this picture on the left of the sun, where you have the many colors of the different that's emitted from different areas of the sun, in fact, despite it being continuous like a rainbow, each light is emitting its own wavelength. It's very discrete in that way. And the sun, in fact, emits at all wavelengths. Another thing about light is that it typically travels in straight lines or rays. Think lasers, like this optical picture down here on the right. So light gets emitted and it gets sprayed in straight lines, but the sun directs it everywhere. Now, light also is very important because it interacts with things. So it interacts with matter, and it interacts with that matter in very diverse ways. Think about reflection from a mirror or transmission through a window. Think about how it gets absorbed in your skin, or even how it gets emitted by a light bulb. All of these different ways that the light interacts or is created from matter depends on the energy of that system and the energy of the light being emitted. So today, let's focus on how a solar telescope treats light. For us as for me and for us doing solar astronomy, the key thing about light is that the sun's light can tell us about features on the sun. In fact, it's the type and the form of matter that last interacts with that light when it comes to us that tells us so much about what's happening on the sun and how the sun is evolving itself. But the other side of that is that we have to collect the light and we have to understand the energy components of that light. And for us, that's what we use the solar telescope for. So we use materials, matter, on the other end to collect the light that the sun emits. And we use the technologies that we have available on Earth to analyze that energy content from the sun. And for us, we're very excited that we have this large new solar telescope on Maui to be able to do just that. So if we take a look and take a peek inside this telescope, it's a very complex animal, but it might not be like some telescopes that you might otherwise be aware of. So inside of it, there's this large dome, and inside of it, there's a mirror that collects the light. And again, you can see the light coming down kind of in a straight beam. This is the straight rays coming from different spatial areas of the sun. But then we collect all of it with a large mirror, and we bend the light into a focus. And then that light gets directed downwards into the telescope into instruments. So we could talk about very many different components of this rather complex instrument in order to how to study the sun. But right now I'd like to take some time to focus about the key component, the very first component that we use to collect the light, and that's this mirror. So DKIS, which is the Daniel K. Inouye Solar Telescope, uses a very big mirror. It's 4 meters across. It's very highly polished, and it's coated with a high quality aluminum. And this is the key component of the telescope that we use to observe, which is another way of saying take pictures of the sun. And I'm often asked, why such a big mirror? Well, if you're familiar with telescopes, one of the reasons you need or even cameras, one of the reasons you need a big camera is there's something called diffraction. And the diffraction is something that limits how nice of a quality image you can take and what's the smallest thing you can measure. So if you want to look at something very, very small, you need a relatively big lens or a big mirror to look at it. But that's not the only reason. And sometimes people are surprised by the second reason. The other reason is light collection. And you might think, well, isn't the sun very big? Isn't it very bright? Well, would you be surprised to hear that the sun can actually be quite dark to us and that we need as much light as we can get? Well, this is the question I want to think about a little bit today, and that's how big of a mirror do we actually need to study the sun? So in order to answer this question, we got to think about the light. We got to think about the content of the light and the energy of the light. We have to know how big the sun is and how bright it is. So to get at this question, let's first consider how big the sun is. So this is a picture of the sun today, taken in just white light. This is if you had a filter or some eclipse glasses and you were able to look at the sun safely, this is what it would look like today. It's mostly a blank disk. Mostly a blank disk with a little spot up here, which is a sunspot. Now, how big is this? Well, in fact, the sun is quite huge. So if you were able to stack Earth across it, you could put 109 Earths right across the diameter of the sun. That means the sun's diameter is 1.4 million kilometers wide. So how we've answered how big is it, how bright is it? Well, this is actually a very important question and one that doesn't have a singular answer. The sun today is not the sun that it was yesterday, and the sun yesterday was not the sun it was a year ago. The sun evolves. So back in 2014, at a time where we call solar maximum, the sun had not just one little sunspot on it, but it had a great many sunspots, or what we call active regions. So these active regions actually influence how bright the sun is, and the sun's brightness changes by a fraction of a percent over its cycle, which is about 11 years. But I haven't answered yet this question of how bright the sun is. So to do that, we need to talk about the energy of the light. So how much energy does it put out? Now, I hope that there's some students involved today, so I want to show some numbers today, but I don't want to scare you with the numbers, because the numbers get so big and so small that we need some special tools to understand them. So to do this, we're going to use, sorry, I think I skipped a slide. There we go. To answer this, we need some very, very simple math. We need to be able to use multiplication to division, but we also need to use something called scientific notation. This is just, don't let it scare you, but it's a way to write some very big and some very small numbers. So if you see something that I write that says 1 times 10 with a 5 behind it, that means a 1 followed by 5 zeros. So 1 times 10 to the 5 is 100,000. Similarly, if you put 10 to the 10, it means 10 zeros, or a 10 to the 26 means 26 zeros. So the bigger this number is, it grows exponentially. It grows to be a very, very big number very, very quickly. Similarly, if I put a negative sign on it, it means a very small number. So -1 means you put the decimal point in front of the 1 by 1 place, and that means 1 divided by 10. Or 10 to the minus 10 means you put 9 zeros in front of that 1, and you get 1 over this huge number. So with that, let's talk about how bright the sun is, how much energy the sun is. So we've measured this with something called a radiometer and calibrated it. We now know that the sun on average puts out 3.8 times 10 to the 26 watts, watts being a unit of energy flux. So this is a very, very huge number, and we have a hard time understanding what this number actually is. So a watt is actually a joule per second. So we can say a watt, this number in watts is actually 3.8 times 10 to the 26 joules per second. But what's a joule? Maybe many of you are not familiar with it. Well, a joule is just a way to measure energy. And in fact, we often think about how much energy food has, and in the US, we talk about calories. But in other countries, you might measure the same type of energy content of your food in joules. And in fact, this is something from Britain, where a package of rice has the energy value listed in calories, but also in kilojoules. So a joule is just a measure of amount of energy. And watts is a measure of energy per time, much like calories are actually energy per serving in that sense. Now for the sun, all of this energy, this great amount of energy, is all being generated by nuclear fusion in the core of the sun. And when it's first generated, it actually does come out of the sun via light, via radiation. And it takes a very long time for that light actually to eke out, or to leak out of that inner core of the sun, until it finally gets to a point where the light is not effective enough in moving the light, or moving the energy. And then all of a sudden, instead of light being the main source of that energy transfer, the sun begins to kind of boil. It becomes convective. And after that energy then comes to the surface, it's emitted as light. So that process from the core to the outer edge of the sun takes about 100,000 years. But once it hits the edge of the sun, where the density has dropped enough that the light can escape, it takes only then 8 minutes for that light to get to Earth. So this is still a very huge number, and it's hard for us to understand these huge numbers, what they really mean. So let's compare it to something that we know better. Well, let's talk about energy. Now that we're on the day of light, let's talk about energy that we use as humans on Earth across the globe. Well, in 2018, if you look up the statistics on energy use, the total amount of energy that humanity used in that year was 4 times 10 to the 20 joules. That's 4 with 20 zeros behind it. So this number is a lot smaller than this number. And we can ask, how long does it take for the sun to output this energy? Well, we can divide this number then to get that. So if we take this, how much we use per year divided by what the sun gives out per second, we can come up with a number of seconds that the sun would take to generate this energy. And it's 1 times 10 to the minus 6. This is a very small number now. It's 1 divided by 1 with 6 zeros, so 1 over 1 million. So the sun, in fact, creates enough energy to power our entire world for an entire year every millionth of a second. That's really incredible to think about. Now, okay, so back to our original question. The sun is very big. The sun is very bright. Then why does DKIST need such a big mirror? Well, we can put this into other terms that we think about as well. It's not only a question of why does DKIST need this big mirror, but why do we need so many solar panels in our house? The sun creates enough energy for the entire year every millionth of a second. Why do we need so many solar panels? Well, it's a clue. There's a clue. Not all of the sunlight that emits from the sun is coming to us directly. So we can't collect all of the electricity at all times. We must use our tools that are of different sizes to collect that amount of energy. So let's take the example of solar panel. Well, first let's think about the sun's energy and recall that it's not all of the energy that gets to us, but we can ask how much that energy does get to us. So the sun's energy emits in all directions in 3 dimensions around it. So that 3.8 times 10 to the 28 joules per second emits everywhere. Not all of it gets to Earth. Earth is 100 million miles away from the sun. So we only receive a very small fraction of this. Actually, we receive only 1,000 joules per second per every square meter on the sun, which is about the size of a solar panel. So a solar panel can collect about 1,000 joules every second. So the analogy here is that the grocery store might have 1 million calories of rice this month, but only 2,000 of them go to your house, So we can ask now, how many solar panels do we need to power our house if this is the amount of energy the sun gives to us? Well, I'll give you an example about my own house. So my family of 4 used about 500 kilowatt hours of electricity last month. We can convert this number into joules. So this amount of energy that I used is equivalent to 1.8 billion joules. So how many solar panels do I need? Well, one solar panel gets about 1,000 watts. That's 1,000 joules per second. But it actually can only absorb a fraction of that. It can only absorb 200 of those watts. This is 200 joules every second. So we can use our division again. So 1.8 billion joules divided by 200 joules per second gives you 9 million seconds, which is equal to 2,500 hours. So it takes 2,500 hours for one solar panel to give me the energy that I need for a month. But unfortunately, there's only 30 days in a month. And in those days, you can only get up to about 10 hours of sunshine every day. So that's only 300 hours of sunshine possible per month, which means one solar panel doesn't give me enough energy. We need more solar panels. We need at least 10 solar panels in order to collect this amount of energy every month. We need it even more when it's cloudy. So based on that, we can kind of understand why a house like this has the number of solar panels it does. It has tens of solar panels of this size in order to collect enough energy to power a house every month. So now the question is, why does the telescope need to be so big? Well, the telescope, it's a different question. We're not using the energy to power the telescope. What we're using is the energy to make a good photo. So to make a very good photo, we need enough light. Everyone who tried to take a picture in the dark knows this. And it's the very reason that most cameras come with a flash. So in the very dark, you need a flash in order to send out light into your scene that you're trying to take a picture of, so that you get enough light reflected back into your camera to take a nice picture. Well, so we need light to take a good photo. Light equals energy. So we can ask, how much energy do we need to make a good photo? It turns out a good photo, if you say a good photo is one that's not grainy and something that looks very nice, it needs actually a very tiny amount of light. For a good photo, you only need 10 to the minus 15 joules. That's one per one with 15 zeros behind it of a joule. That's a very, very tiny amount of energy in the scheme of things in order to make a good photo. So for the sun, we need to collect this energy within a few seconds because things on the sun are happening very fast. So we want to take a photo of the sun before it changes. So this is the context that we can answer this big question of why does our mirror need to be so big? So surely though, DKIS can get this amount of energy, right? I mean, a solar panel gets 200 joules every second, and all we need is this one times 10 to the minus 15 joules. Surely it can do it. Well, there's more things that we haven't said that make this number smaller. So let's do what we call an energy budget in terms of to try to figure out how big our telescope needs to be, or rather, if DKIS is a big enough mirror. So we start with the sun giving out this amount of energy, and we need this amount of energy to take a good picture. So first, we know that we don't actually get all of this energy. Only some of that goes to Earth, and only some of it is collected by DKIS. A solar panel gets 200 joules a second. DKIS, with 4 meters in diameter, gets about 12,000, 13,000 joules every second. Well, this number is still very much bigger than this number. So what else is affecting our picture? Well, it happens that we're not trying to take a picture of the full sun. We're trying to take a picture of a very tiny piece of the sun. So we have to account for that. So DKIS is not trying to look at the full sun again. It's taking a resolved picture of very tiny pieces of the sun. Pieces of the sun only 30 kilometers on a side. So we need to take the area of that little piece of the sun and divide it by the area of the sun to get the fraction of the sun that we're looking at. And that turns out to be 6 times 10 to the minus 10. We multiply this number by this number, and what it turns out to be is we get this amount of energy now for our little piece of the sun. We only get 7.5 times 10 to the minus 6 joules per second, which is a much, much smaller than what we started with, but still a lot bigger than what we need for a good picture, right? So minus 6 is much bigger than minus 15. So what else is coming into play? Well, now we have to realize that the sun has many colors. We talked about light at the beginning. Light has many different energies. It has many different wavelengths, and that means it has many different colors. And that color tells us a lot about what's happening on the sun. So we're used to, when we, on Earth, especially out in here in Hawaii, we're used to the many colors of the sun. We know a lot about the colors of the sun. So, and we were reminded of that every time we see a rainbow. So rain droplets in our atmosphere can disperse the light of the sun. So the white light of the sun gets broken up into its many colors of visible light from blue to red. Now, if you take that same rainbow and you have a very, very special instrument in order to not look at all of the colors like this at one time, but rather blow it up and try to look at very, very tiny slices of the rainbow, you get something that looks like what's on the right. This is the exact same rainbow here, but stacked in energy for each line. So imagine this rainbow, unstack this picture and make it a huge, long, wide picture of the rainbow. And this is just the rainbow stacked. And what you see in this rainbow, and this is from the sun, is that the colors are not continuous. In fact, what you get is these little dark lines. So in the red, you have this very dark line here, this dark band, and in the blue, you see all of these many, many lines. These many, many lines are actually telling you about little discrete emitters of light of a particular wavelength. And they're actually corresponding to different atoms of different elements in the sun. So this line, for example, this little dark feature tells you about hydrogen on the sun. These lines in the green are telling you about sodium. Different elements create these different lines. So for a solar telescope, we don't want to look at all of the light. We only want to look at these little bitty lines of energy in order to understand that particular element on the sun, and that element and the gas it comes from and the temperature of it. So back to our energy budget. So we still have a lot of energy, but now we know that the sun has many colors. And a DKIS camera doesn't look at all those colors at one time. Instead, it looks at 1/1,000,000th of that rainbow at a time. So if we multiply this by that, we get this number. So we get 10 to the minus 12 joules per second, which again is still bigger than our number here. So we're good. So we can look at pictures of the sun with very, very small spatial sizes, with very tiny pieces of the rainbow, and still get a good picture every second. So what's left? Why does our mirror need to be big again? Well, the last little bit has to do with what's called polarization. So the light of the rainbow is not only just the intensity of it, it actually, like a wave, the wave can be directed in many different ways. And that's called polarization. And that polarization tells us a lot about what's happening on the sun. It tells us about magnetic fields. It tells us about scattering. It tells us a lot of different things about the sun. But it's also very weak. That weak polarized piece of the light is only about 1,000th or 100th of the total light. So we have to divide this number again by 1,000 in order to get what the actual measurement of light we're trying to get. And when you do that, you get 7.5 times 10 to the minus 16. All of a sudden, our number has gotten smaller than this number, which means it takes us a little longer than a second in order to get a good picture. This is exactly why DKIS has to be as big as it is. It has to be that big in order to collect enough light to measure at the tiny pieces of polarized light at a particular wavelength for a particular piece of the sun. So this big mirror that has been designed and put into DKIS observes the smallest features on the sun and the tiny pieces of the light spectrum and its polarization. But it would be a shame if DKIS only did this for one single wavelength of light, to collect all of that energy only to look at a tiny little piece of it. Doesn't tell us as much as we could learn about the sun. So DKIS, one of the very special things about DKIS is that it's also designed to observe many wavelengths simultaneously. So we could talk about much of this, but I just want to take you through a quick tour of the rest of the telescope. So we've talked a lot about the big mirror that collects all the light, but then that light gets directed downward. So the first thing it interacts with is the top of this telescope. So, which is up here at the top of the dome. So the light comes in, it bounces off of this big mirror, which is shown here on the telescope mount, and it's directed to another mirror up here called the secondary. The pieces of the sun that we don't look at, actually we reflect off with a heat stop in order to get rid of the heat. And on this date, that light was directed into the dome itself. So now we capture it. But the rest of the light comes into the telescope and is directed downwards into the belly of the beast, so to speak. And the first thing it goes through is down here in the bottom of the telescope is this big rack that we call the Gregorian optical station. So it's the secondary focus, and it's where the telescope creates its first really nice focus. It's the second focus of the telescope. And here we have a lot of optics that go in and out of the light path in order to calibrate both how good the image quality of the telescope is, and also the polarization properties of all the telescope optics behind this point. And this is just to give you some sense of scale. This little box is deeply embedded here, and then one of our optical engineers is here standing next to it up at the telescope. Now from there, the light continues down into the heart of the telescope, and that's where all this instrumentation lives. And on the International Day of Light, this is probably the most exciting bit in terms of technology to talk about, because this is where all the light comes in and it interacts with all of our lenses, all of our filters, and all of our cameras, so that we can collect that different energies and different polarizations of the sun. So on this big table, which actually rotates throughout the day, we have 5 instruments. And in these instruments, we have more than 14 cameras. And many of these can look at different pieces of the light coming from the sun, different colors, and most of the time operating all at the same time. On any given day, these cameras are taking up to about 500,000 pictures of the sun every day. And every single one of these instruments has a great amount of very advanced optical instrumentation involved with it. So we're pushing in every instrument the limits of current technologies, whether it be for lenses and mirrors to collect and guide the light, or for coatings in order to separate the light into different colors, or for filters in order to block out light that you don't want, or to select the light that you want, or fiber optics, and even cameras, which have to be specially built for what light you're looking at, whether it be visible or infrared. So back to this statement at the beginning. At the Solar Telescope, we do a lot to study the light as it has been emitted from the sun in order to understand how it was emitted and how it last interacted with the solar atmosphere. And we use all of this great technology in order to collect that light and analyze it. So in the last couple minutes here, what I'd like to do is now tell you a little bit about the science we're trying to get at and show you some of the images of the sun that we collect with all of this technology and this big mirror. So you've maybe have noticed this big image on our website or in the news. It made a great amount of news last year about the very first high resolution image that the Daniel K. Inouye Solar Telescope was able to take. And again, we don't look at the entire sun at any given time. There are telescopes that do, but DKIS is looking at the very tiniest details on the surface of the sun. So this is a picture of the full sun in the background taken by a separate telescope. And the embedded image here is the size of one of our cameras. So one of those 14 cameras can take an image about this size of the sun. And in this image, if we select just a little piece of it, this is the kind of the quality that we see, the features that we can see on the surface of the sun at that high resolution. So again, I said earlier that the energy that's coming from the core of the sun leaks out first radiatively, and then it gets into the convective zone and it boils. Finally, once it reaches the surface, what you see is this convective energy overturning and creating different patterns. So this is almost like a boiling pot of gas, convective gas, overturning and changing all the time on the sun. So these little parcels of gas like this are actually about the size of Texas, or the structure in between of it can be the size of the skyline in Manhattan. These things are changing on timescales of every few minutes to every 10 minutes. So what this huge thing the size of Texas is completely washed away after 10 minutes. That's how fast things are happening. Now, embedded in this convective granulation, what we call on the surface of the sun, is magnetic fields. And that's where a lot of the energy resides that we're interested in for the solar atmosphere. And in this particular picture, that magnetic field is shown to us in this bright filigree or this bright pattern of plage. So these little bitty tiny things that are very, very finely structured are actually tracing magnetic field. And one of the key questions for the Daniel K. Inouye Solar Telescope is exactly how those surface magnetic fields get generated and how they impact the energy content of the atmosphere and also the evolution of the sun itself over long time periods. So DKIS will actually measure these magnetic fields on very small scales to understand how they evolve and to study effects like what we call the local dynamo. Local dynamo is something that actually can, through the convective motion, can take a small magnetic field and amplify it. We're also interested in how this convective motion pushes around that energy and transports it to different pieces and different regions of the sun and influences the larger dynamo, the global dynamo. And we're also interested in how that energy gets transported upwards into the atmosphere, which we'll show in a second. But in addition to small things, we're interested in how the sun organizes its energy into bigger scales. So what we see here is one of those small sunspots that we looked at earlier. So on this date, the sunspot was here. It's about the size of Earth. And this is the very first picture of a sunspot that the Daniel K. Inouye Solar Telescope took. And what we can see is the amazing detail of this large concentration of magnetic field. Now, this is just the tip of the iceberg in terms of what the images of DKIS will be. So let's look a little bit at some of the data from a previous telescope and what we can expect coming up. So this is taken from another telescope in New Mexico called the Dunn Solar Telescope, showing you again that convective motion, but this time with the sunspot itself. And this is an active region of the photosphere of the sun. And DKIS is going to measure and study these quite a bit because these active regions have a lot of energy, and that energy can get released into space and impact Earth via things called flares, solar flares, and eruptions. But let's concentrate on what we can see just in this picture. What we are seeing is actually gas that's emitting at a very particular wavelength at a very particular temperature. The temperature here is about 6,000 degrees, and what you're looking at is actually iron gas, mostly. This is actually taken in the wing of one of those little bands in the rainbow. But this scene, what you're seeing here, looks completely different at a different wavelength. If we go to a wavelength at 656 nanometers, a wavelength that's hydrogen, and that's formed a little higher up in the atmosphere than this photosphere, this is what you see. You see something completely different. What was this granular pattern is now a fibril pattern. What looked like bubbles now has these long features of filaments. The sunspot now has a huge extent. It expands out. And also something has changed a lot. This is called the chromosphere. The temperature has changed from 6,000 degrees to 10,000 degrees. This is a huge puzzle that we are still trying to solve in the sun, is why when you go higher in the atmosphere, does the atmosphere get hot? On the surface of the Earth, we're used to, if you go to the top of a mountain, the temperature usually goes down. At the top of the summit of Haleakala, where DKIST is, it's usually many degrees cooler than it is down at the beach. So why the chromosphere of the sun gets up to this very high temperature remains a puzzle. It's related to those little magnetic field concentrations, but we still don't know how it exactly happens. And it's this multi-wavelength polarimetry that DKIST will use in order to study this question. But the puzzle goes more. It goes farther from there. If we go higher still in temperature and in height, we look at what's called the solar corona. And this is a picture actually not taken from the ground. This is taken in ultraviolet light, which is a light of very high energy that you can only see from space. So this is taken from a satellite. But what you can see now is that pattern of the granules, that bubble on the bottom of the photosphere, and those fibrils in the chromosphere has now been transplanted into a whole nother pattern of extended high temperature, bright loop-like features. This light is telling you that this gas is emitting at 1,000,000 degrees now, not 6,000 degrees like the photosphere, but now it's 1,000,000 degrees. How that temperature is created is a key part of this problem that DKIST will be trying to understand. But DKIST can't look at ultraviolet light. It has to look at visible and infrared light that gives us a measure of this corona, the solar corona. And that's something that's very special about DKIST. So DKIST, normally if you look at visible light, you only see this sun. This is taken a picture of the sun in 2017 where you can see sunspots in the center of the sun. And normally if you look at a solar telescope, this is about what you can see, where the blackness back here is just the blackness of space. Or if you don't have a telescope, an ice telescope in space, you would see the blueness of the sky. Now, DKIST is able to actually create fake eclipses. We can block out the sun on the disk of the sun so that we get a picture of the energy that's being emitted around the sun. So it turns out that the energy around the sun is there, but it's about 1,000,000 times weaker than this disk of the sun. So we have to block out that sun in order to be able to see it with our cameras. And that's what we do. And what we can expect to see is something like this that we see at an eclipse. What we see, instead of just the round disk of the sun, is we see an extended hairy ball of energy reaching out into space. So what you see in this beautiful image here is actually, you see the moon, the surface of the moon blocking the sun, and you can see those magnetic fields coming out of sunspots and coming out of the surface of the sun, extending well into space. And one of the key science missions of DKIST is to use this enormous amount of light that we collect and all of this highly advanced instrumentation in order to understand and measure the polarized light coming from this, so that we can map how the energy of this low part of the corona actually extends into the solar system, what we call the inner heliosphere, and how that influences our Earth and other solar system bodies. So with that, we've done a lot in this talk. We've talked a lot about light. We've talked a lot about the collection of light. We've talked a little bit about instruments, and we talked a little bit about the science. If I could leave you a little bit with a summary, I would just go through our top level points, and that's light is energy, and the sun emits a lot of it, and it emits it at all wavelengths. That light of different wavelengths interacts with matter in unique ways. This lets us learn about distant objects, and it also lets us use that light to build technologies for different purposes in medicine and in light science and in communication and every other industry. So the optics and other technologies are very useful because that's what helps us as solar astronomers observe the different properties of those wavelengths emitted from the sun. And it turns out we need a very big telescope to collect enough light to see those many colors. DKIS allows us to look at the very different pieces and different temperatures of the sun and to learn about the things on the sun, how they work, how they evolve, and how they impact our Earth. With that, thank you very much for your attention. And I hope you have a chance over the weekend to celebrate International Day of Light yourself. And please, I welcome any questions you might have.
Thank you, Tom. Great talk. I have a question here. So Mick from the UK says, I'm a solar enthusiast and observe I'm a solar enthusiast and observe and image the sun in all wavelengths. My favorites being H alpha and calcium K. Question is, does DKIS take any H alpha or calcium K images?
Yes, in fact, those are very prime diagnostics of the chromosphere of the sun. So that picture that I showed of 10,000 or so degree plasma, this picture here, this pink, is actually taken in H alpha, not from DKIS, but from the Dunn Solar Telescope. But DKIS has many instruments that will measure both of these lines. The instruments vary in their technology. Some take images, some take spectra, some take polarized spectra. So we have the capability of taking high resolution images with filter-based instruments of H alpha and calcium K, but we also have spectrographs that are able to take high resolution spectra. That's the dispersed rainbow across regions of the sun. So yes, those two wavelengths are very important to us.
Thanks. Another question. How does the telescope look at only some of the rainbow rather than all of it?
Great question. So again, this is, we're using technologies that are very new in order to filter out lights to take particular images. So an image like the one you see here in pink is using a filter, which is really just kind of a piece of glass, but it's coated with a special coating, sort of like if you've ever had, glasses with anti-reflection coatings, so that whenever somebody takes your picture, you don't see the glare of your glasses. We use very special coatings in order to reflect those lights, those wavelengths of light that we don't want to see, and transmit what we do want to see. That's one way to separate the light. Another way of light separation is what's called a dispersive element. There's many different things that you can use to do this, but one thing is called a diffraction grating. So it's kind of a big piece of reflective metal that has lines across it that are etched by a machine, and that etching actually helps create a rainbow, just like light, just like water in the sky creates a rainbow on a rainy day. We use something that does the exact same thing to spread the light out at very high resolution, and then we can put our camera in the rainbow where we want it. Thanks for the question. Great one.
Okay, I have one more here. It's, why do you want to look at such tiny pieces of the sun?
Right. So the tiniest pieces of the sun are very important, it turns out, to the total energy of the sun. So although, oftentimes when you think about flares and you think about sunspots, these big manifestations of energy in the sun, like this picture here, you think that that's where all the energy is, but in fact, a great majority of the energy is in those small scales. So the magnetic energy, if you add up all of these small scale magnetic fields across the sun, there's a lot of energy there. And those little traces of the magnetic field that are organized on these tiny scale is what then transports energy to different pieces of the sun. So that energy that starts out in the photosphere where it's boiling can actually use those tiny little magnetic fields to transport that energy high up into the atmosphere where it gets hot. And where it gets hot, it emits ultraviolet radiation. And ultraviolet radiation interacts with our Earth in a particular way. So for us to study the magnetic field on these tiny little pieces is to be able to study how energy actually gets transported in important ways in order to energize the atmosphere as a whole. I hope that answers your question.
That's really cool. Great response, Tom. I think that's all the questions we have for now. So with that, thanks again, everyone, for joining us. And thank you, Dr. Schad, very much for being here.
Great, and thank you to Shauna, and thanks to everybody.